In this video, I'm going to show you how to conduct a one-way ANOVA in R. So again, we're going to use the same example that we did for our computational videos. And so what we have are three different treatment conditions where participants are exposed to either 50 degrees, 70 degrees, or 90 degree temperatures. And we have 5 participants in each of these conditions. And the dependent variable here is how many problems that they were able to solve in these different conditions. All right, so first thing we need to do is create a temperature vector that's going to represent our 3 different conditions. And we use the concatenate again to put all of these individuals together. And so we have 3 conditions, each with 5 individuals. And so the first individual here is in a 50 degree condition, 50 degree condition, and so on and so forth. The next 5 are in a 70 degree condition, and the next 5 are in the 90 degree condition. Note that 50, 70, and 90 are all in quotation marks because they are categories, not values. And we need a second vector for our dependent variable. That's the number of problems that are solved. So I'm going to call it solved. And again, we're going to use a concatenate to put all of these values together into a single vector. So here we have the first 5 individuals, 1, 2, 3, 4, 5, who were in the 50 degree condition. And then the next 5, 1, 2, 3, 4, 5, were each in the 70 degree condition. And then the last 5 were in the 90 degree condition. So it's important to note that these values are lining up. So the first individual was in the 50 degree condition and they solved 0 problems. The second individual was in the 50 degree condition and solved 1 problem, and so on and so forth. All right, so next I'm going to create a data frame called temp data, or short for temperature data. So I'm going to name the data sheet after my independent variable, and I'm going to use the data frame function to create it. And I'm going to take the temperature vector and the solved vector, and I'm going to put them together into the data frame. All right, so let's have a look at what happens when we execute these 3 lines of code. So once we execute the first 2, we can see in the global environment we have 2 new vectors. And when I do the third one, now we have a data sheet with 15 observations and 2 variables. If we want to take a look at it, so just type in the name of the data sheet, and here we are. So we have our 15 individuals, the temperature condition, and the number of problems each of them solved. Okay, so there is a function called analysis of variance, or AOV, and the way that you structure it is similar to the independent samples t-test. You identify your dependent variable first, solved in this case, and then you use a little squiggly line, right, is dependent on, and then your independent variable, in this case, temperature. And you have to tell R where the data is coming from. The data is coming from our new data sheet called temp data. All right, now, if I just execute this code, we're not going to get too much information. We get the sum of squares for temperature and for the residuals, and we get the degrees of freedom, and not much else. We're also told that the residual standard error is 1.15, but what we really want is an ANOVA table. So what we're going to do is we're going to take this command, we're going to put it inside of the summary function, right? So notice that this is all exactly the same as line 141. All we've done is we put it inside another set of brackets and with the function summary. And if we use this, execute this code, then we get exactly what we're looking for, which is the ANOVA table. Temperature, that's our between subjects effect. That's the thing we're interested in. Residuals, that's the within subjects error. And so we can see the between subjects sum of squares is 30, and the degrees of freedom between subjects is 2. 30 minus 2 gives us a mean square between of 15. The within sum of squares is 16, divided by the within degrees of freedom, which is 12. 16 divided by 12 gives us the mean squared within, which is 1.333. To get the value of f, we take the mean squared between, divide it by the mean squared within, and that gives us 11.25. And finally, we can see that this is a statistically significant result. This is our value of P down here. If we compare that to our computational example, we can see that it is exactly the same. All right, so the problem, of course, with a one-way ANOVA is it tells us there's a significant difference somewhere, but it doesn't tell us exactly where to find it. So recall that in the computational example, we used Tukey's HSD, or honestly significant difference. And we can do the same thing in R. So again, notice that this inside bit here, that's exactly the same as line 141, right? All we've done is we put it inside brackets, and then we've added the Tukey HSD function. And if we execute that code, then we see the differences between our three groups. So if we look at the 70-degree group minus the 50-degree group, it's a difference of 3. And we can see the 95% confidence interval with 3 at the middle of that confidence, and then this lower boundary and the upper boundary. Notice that it does not, the value of 0 is not contained in this interval, and that's an indication that we have a significant difference. But we can just look at the p-value. If we just look here at the p-value, we can see that it's less than 0.05, and that means that the 70-degree group and the 50-degree group are different from each other, significantly different. We can see that the 90-degree group and the 50-degree group are not different from each other, looking at the p-value. And the p-value for the 90-degree group versus the 70-degree group is, again, statistically significantly different from each other.